What makes you think that there may be some way to prove it without when additivity is not there? It looks like a hopeless situation. I mean, you obviously have some idea.
No, I don't want to say I have an idea. It's a question. I mean, I think it's a good hypothesis to think that the strong converse might hold, simply because the noise is independent. Of course, this intuition may be wrong, and this would be equally exciting to know that because of using entanglement, you can increase somehow you can somehow get a trade-off between error and rate. But it's probably it's more a hope that because for many channels we know that it's true. In the classical world, it's kind of almost a given that it ought to be true here as well. And the fact is, we know in some cases how to prove strong converses without directly referring to additivity. So one example is the entanglement-assisted capacity of a channel. Thanks to the reverse channel theorem, we know that both of them obey a strong converse because they limit each other, vice versa. So this proof by appealing to the reverse channel theorem, it doesn't use additivity in a direct way. It somehow pops out at the end, and you might speculate maybe it works only because we have this tight characterization, additive characterization. But the fact is, we only know strong converses to hold after we know the additivity of the channel, even if the proof doesn't directly appeal to it.
In the special case of this entanglement breaking and Hadamard channels, is it possible to identify at least a small portion of encoding states to identify them, which can be decoded with fidelity greater than 1 minus some lower bound there?
So you're saying you want to, rather than decoding a single message, you want to go for a subset? Or did I misunderstand?
No, this is generally getting estimates for the lower and upper bounds in the case of channel. But
yes.
Can we identify some small portion of the encoding space where the states, if I take them as input states, and from the output, can you make the decoding arrangement with fidelity,
yes.
fidelity greater than some delta positive?
Well, there are certainly such sets. I mean, for example, if you restrict to product states, then we can characterize this relation very tightly. But in general, I doubt this is easy.
Something like approximating the nil-Flam theory of instead of exactly error-correcting codes.
But that's exactly it. I mean, this is channel theory. This is all approximate. I mean, the epsilon is exactly there for this purpose. It's to quantify how much error we allow.
Yes.
And so this whole subject is about the possible trade-off between epsilon and how much information you can have. So when you prove a strong converse, it kind of puts a stop to this sort of idea, because it shows that asymptotically there is none. There's nothing you can gain. It's almost as if you have no error.
The second order thing you're referring to, what information, additional information it would provide? And is it related to the channel dispersion?
Yeah, okay, I had it on the slide, but I didn't mention it because I thought it would lead too far. I mean, I suggest we take this offline. I mean, it's exactly like this. It's an even refined statement, even going beyond this, to understand the rate even better.
So we thank and welcome Andreas again.
All right. Yeah, again, can we shoot this one? Yeah, I think it's much better. So yeah, so what I really should do is I should try to impersonate Runyao, but I neither in style nor in stature I can emulate him really. I mean, you should try to imagine a man about 10 centimeters taller and about in all directions 10 centimeters wider than me, with a large booming voice and a beautiful South Chinese accent, if you can. So luckily, let me start again. So unfortunately, Runyao experienced some difficulties coming here because the visa application that he had was delayed. Fortunately, he got the visa only the other day, but unfortunately by that time he couldn't find any flights anymore that would get him here in time to deliver this talk. So he sent me the slides and he said, look, I mean, we did this work together. For sure you were able to deliver the talk, and I admit I should be able to do that. So let's see what he prepared for us. So the topic of this is this very long and unwieldy title. It's always communication, of course. When you listen to me, most of the time I will talk about communication. But in the zero-error regime. So we are going away from this Shannon theoretical approach of small errors going to zero in the limit. We want to have error exactly zero. So this was something that was invented by Shannon a few years after his famous paper. He has a slightly less famous paper. So it's still the same game, but we add another twist to it. So in the spirit of all these, for example, entanglement-assisted coding and whatnot that we know in the world of quantum Shannon theory, we allow a free resource that Alice and Bob can use, which in itself doesn't allow them to communicate. These are the so-called non-signaling correlations. So I will start first with a sort of a general overview of channel conversion. So this is something that maybe we should have put a reference to an old paper by Reinhard Werner, who popularized this, and then of course also Charlie Bennett even before. So somehow the correct, or the physicist's way of looking at information theories is that, for example, these channels, they are some kind of resource, a costly one. This is part of your world. So you can draw at a certain price at things like n. Or, I mean, it doesn't have to be a channel, but for the purpose of this talk, it's a channel. And there is something that you desire. In this case, it's another channel, m. Unfortunately, very differently looking from n, so you cannot just trivially modify the first one and get the other one. Luckily, in your world, you have also somehow access to other things, which are so cheap that let's consider them for the theory as free. For example, usually in the theory of communication, we allow arbitrary encodings and decodings. So these are local operation of Alice on her end and Bob on his end of the system. But these free resources, they might also be other things. For example, free entanglement or backward communication or whatever. Or you might be able to borrow some resource from the bank, but you have to give it back later, unchanged. So there would be catalysis. So this is kind of the larger picture. And information theory is about how efficiently can you do this desired conversion. So you have something that is valuable to you and something for which you have to pay. So, and you are interested in, first of all, can you at all convert, let's go to channels now, a channel n, via using these free resources omega, whatever they are, to a channel m. And so here are some examples of this. Some of them I said already. So here the E is the one, D is the one that we are considering in this talk, no signaling correlations. And so in particular, we are interested in the case that you can exactly transform it. But of course, in the real world or in the applied world, we might as well also consider a conversion with some approximation. So of course that means that whatever procedure you have that involves the channel n and some other resources to get m doesn't actually give you m, it gives you some m prime. And then you need this epsilon to quantify a distance. So this here implies also that you have a notion of distance between your channels, which I skip here for the purpose of the talk. So then the information theory comes about when you have many uses of these things. So then you can talk about rates, and so you divide n by m, so you want to minimize this because you want, for given m, you want to use as few resources that are priced as possible. And so this is the zero error information rate of converting n to m with free resources omega. So this is a very Baroque notation maybe, but just to give you the flavor of that, this is actually just a special case of a very, very general theory that you can build. And the same for small epsilon, and then of course in the limit we should let epsilon go to 0. So the beautiful thing is this includes a lot of interesting problems, but of course two that were considered before and that are of paramount importance in information theory. The first one for sure, since Shannon, it's the communication capacity, where we want to convert the channel n to some ideal channel. For example, a perfect classical or qubit channel. And so this rate here is actually just the inverse of the capacity. It's like the capacity as how well can you transform n into identity. And the opposite is if you want to convert the ideal channel into n, so this is this Homer-Simpson problem that Charlie was mentioning or used to mention for many years in the context of the reverse Shannon theorem. And so usually that's much easier. At least it's easier to see that you actually can do it. But of course the interesting question there is how do you do it most efficiently using all of your free resources. And so this is the simulation cost, which by definition, I mean if you do all this correct, this is by definition larger or equal than that one. So in the small error case, our world is beautiful, at least if the free resources include entanglement. So this is thanks to the entanglement-assisted capacity theorem, proved by Bennett, Shor, Smolin, and Tablial 11 years ago, and the quantum reverse Shannon theorem, also due to Charlie Bennett, Igor de Vetak, Aram Harrow, always Peter Shor, and my humble self. So in this case, it turns out that so when omega includes arbitrary entanglement, these two numbers are the same, and that implies, and that's for the non-zero error case. That implies that the transformation rate of any channel to another one is just the ratio of these two entanglement-assisted capacities. So we understand everything about this. And so, yeah, so there's kind of, in particular, the theory is theoretically very beautiful because it means that it's also reversible. So going back from n to m, I mean, it's not reversible on the microscopic level. So if you start with n copies of some channel and you get m copies of another one, it doesn't mean you can go back even approximately. But the rates are the same asymptotically. So you're losing only some kind of lower order amount of your original resource. So this is, I mean, in the spirit of that you have to pay for the valuable resources, this is a theory only for the very rich because it's about asymptotically infinitely wealthy person, right, that wants to convert their wealth into something else. Such people obviously are interested in reversibility because they don't want to lose. Okay, never mind. So let's go to the zero error case. So this is a beautiful theory that goes back to Shannon, as I said, and it's actually very popular. It became almost immediately very popular in combinatorics. I mean, in fact, it opened up various directions in graph theory. That's because of the following. So Shannon formulated this problem for classical channel transmission, and he immediately realized, okay, it's basically boils down to a graph theoretical problem, namely of finding the so-called independence number of a graph. So in those years, in 1956, when he wrote that paper, he didn't know this. Actually, he couldn't because this word didn't exist, but the concept didn't exist, but this is NP-hard. Actually, it's an NP-complete problem if you formulate it in the correct way. In the same paper, however, he also did another thing. He also already started this experimenting with other resources. He allowed free feedback, which obviously by itself doesn't allow Alice to communicate to Bob. It only allows Bob to communicate to Alice. So sometimes that may be cheaper, so maybe we consider this free. And in that case, he could actually solve it completely. He has not only a closed form expression, but it's also efficiently computable. So that emphasized even more how difficult the unassisted problem is. And so, yeah, over the years, I mean, by the time Lovas wrote the famous paper under item 2, the notion of NP hardness and other complexity classes was known. So it was also understood that the next best thing you can do is you can find a relaxation. You can, if you can't compute something efficiently, maybe you can compute efficiently some bound of it. And so introduced the still currently best upper bound, the Lova's number or the theta number, that is a semi-definite program. So, yeah, so then we started taking this to quantum information, and in quantum information, of course, we are used to considering a lot of other resources. I mean, feedback is clearly a very nice one, but it still keeps you in the classical world. So what about entanglement? Now, entanglement doesn't increase the capacity of a classical channel, the Shannon capacity. But the zero-error capacity, maybe yes, because the argument that you invoke to prove that it doesn't increase it, it doesn't apply. It actually relies on having these small errors to give you a little bit of wiggling room. And in fact, a few years ago, some of us showed that entanglement can indeed increase the classical zero-error capacity. Not from 0 to something, so you don't have superactivation, but from some small number to a bigger number. On the other hand, this Lova's number is still an upper bound. It still remains an upper bound on the entanglement-assisted zero-error capacity. So despite the fact that we know that these are different, the Lova's is still above, so there's a clear ordering. And then the last item is a piece of work that actually motivated what we're doing here. So always for classical channels, together with Toby Cubitt, Debbie Long, and Will Matthews, who was then well, just out of his PhD with me, we looked at the case of arbitrary classical no-signaling correlation. So these are the kind of things that various people have mentioned in this conference already, the type of thing like these Popescu-Rohrlich boxes. So non-locality that is only constrained by the principle of no-signaling, but may go way beyond what is allowed by quantum mechanics. The nice thing about this is those no-signaling correlations are just constrained by linear equations, namely basically normalization. Certain probabilities have to sum up to 1 because certain numbers have to sum up to 1 because they're probability distributions, and inequalities. These numbers have to be non-negative because they are probabilities. And so it turns out that you can solve this entire part of the theory by linear programming. So I won't go into this because you will see sort of the analog of it when we allow quantum channels and arbitrary quantum no-signaling correlations. So here are the main results. So I will in the next couple of slides, I will introduce what these, I will show you a little bit what these quantum no-signaling correlations are. And here are the things that we can prove. So we consider using a single channel and trying to communicate, and it turns out, theorem 1, it's an SDP, it's a semi-definite program to characterize how many messages you can send, assisted by the appropriate, judiciously chosen no-signaling correlation. Theorem 2 and 3 are about the simulation part. If you want to simulate a channel N with suitably chosen no-signaling correlation, how many bits do you have to communicate, actually? So this is all SDPs in terms of something that we call the non-commutative bipartite graph of the channel, and in turn, well, actually, this is I feel a bit embarrassed about this because we don't really have a graph theory behind it, but what it really is just the span of all the Krauss operators of the channel, linear span. So it's a space of matrices. So this is valuable because it also teaches you that certain channels, they look very different, but just because they have the same linear span of the Krauss operators, they behave actually exactly the same under the zero error. So then, part 2, we can also find the many uses case. So there are certain channels for which we can evaluate the asymptotic communication capacity. These are the CQ channels. And this is another semi-definite program, interestingly. So it's not the same as the first one because we have an additivity problem, but it's some SDP. And then finally, maybe this is really what we should have put in the title of the paper. But on the other hand, this might be only exciting to graph theorists. Do you see this Lova's number it's just an upper bound on the independence number. Okay, we also know it's an upper bound on the entanglement-assisted capacity, but it's just an upper bound. And apart from the fact that it's convenient, that it's SDP, has many nice properties, nobody really knew what it signifies. I mean, since it bounds a capacity, is it a capacity itself? Can we prove the bound by operational means? Simply by saying, for example, instead of having no resource or entanglement, you have some other appropriate resource, and you get theta exactly as the capacity. And this is exactly what we find here. It more or less as an accident. After doing all this evaluation, we find that for an arbitrary graph, the Lova's theta function turns out to be the minimal, it turns out to be the zero error capacity assisted by a suitable no signaling correlation. So going from entanglement to no signaling, it gives you exactly theta. So now we understand why theta is an upper bound to all these other zero error capacities, because no signaling correlation, they actually encompass entanglement and much more. So it's, as far as I'm aware, this is the first interpretation of the Lova's number as a capacity of something. It really is a vindication of it. Okay, so I'm not sure how I'm doing with time again, so 10 minutes maybe. So here are what are no signaling correlations. So I mean, a diagram would have been nice, but so no signaling requires two parties, and each party has to have an input and an output. So in the classical case, so in the kind of these sort of PR boxes that you might know or might have seen in this conference, a no signaling correlation of the non-local type is basically just a channel, because all that we require is that once the two parties specify their inputs, there should be an output distribution that is also distributed. One part goes to Alice, one goes to Bob. And so the quantum case is basically just replace channel by CP map. It's very primitive. I mean, and again, there should be some references to older work, including Preskill, et al., Reinhard Werner. So it's a channel that has two bipartite input, because Alice can put a quantum state and Bob can put a quantum state. Then pi is a completely positive and trace-preserving map. And then Alice gets an output and Bob gets an output. So that is completely positive and trace-preserving is characterized by the properties of the Choi matrix. It's positive semi-definite. And if you trace over the outputs, you get the identity. And then you can actually, just like in the case of non-local correlations, you can write linear conditions that can encapsulate the fact that Alice cannot communicate to Bob. What does it mean that Alice wants to communicate to Bob? Alice can communicate to Bob if there are two different states she can input in her system that would somehow make a difference for Bob's output. Because Bob obviously doesn't have access to Alice's output directly. And so it turns out this can be also formulated as linear constraints on the Choi matrix. They look a little bit like this. I mean, this is not very illuminating maybe. But again, I mean, this is in complete analogy to the non-local case. No signaling is basically just a bunch of linear conditions on the kind of transition probabilities that you have. So take my word for it that it's actually just a finite list of them. So and here we do, we want to use this no signaling correlation together with the channel. So up to some kind of intermediate local processing of the information, this always looks like this. We always kind of couple together the channel with the correlation. So here we have Alice's part. Alice has an input. So what can she do? And basically you just have to think she has two objects. She has the box and the channel N. And so after a bit of thought, you will realize basically the most general thing she can do is encapsulated in just sticking her state into the non-local correlation. And she gets some output which goes directly in the channel. Again, I ignore some kind of pre-processing or intermediate processing time. Bob gets something from the channel, okay. He used the channel, he has a state, he has a machine, he sticks the state in the machine. That's his part of the non-local correlation. He gets an output. So this AI to BO, that will have to be the simulation of the channel M. And so physically, I guess that should make sense. Runhao was really worried that this makes mathematical sense because after all, the channel pi, it goes like this and like that. And so how can I sandwich another channel between the output of one part and the input of the other part? And of course, because of no signaling, there is no problem with consistency. But you can see this also mathematically. So one way is looking here at this left picture. It's possible to show the following. This pi can be written as a linear combination of tensor products of channels. So yeah, okay, that's, maybe he thought about this differently. I mean, one way you can think about this, AK and BK are actually completely positive in trace-specific maps. And then there are some weights, some lambda k's here that I suppressed for the moment. And so this linear combination is then no signaling, and there are ways of choosing these lambdas such that you still get a completely positive map. So this is it. Okay. So I will just present you the theorems. Probably, I mean, I think the slides contain some ideas for the proofs, but I will skip them because they will lead. The statement of the theorems are a bit hard to swallow, I guess. Let's just go through it a bit slowly. So let's just look at this again. So this is a typical semi-definite characterization. So consider this omega as a variable, right? I mean, eventually we would like to communicate via n optimally, in the sense we want to use the best possible no signaling pi. So that means in our optimization problem, pi is the variable. And to do this mathematically, the convenient way is to write down this Choi matrix, because all the properties of pi that we need are actually properties of the Choi matrix, and they're very nice one. There is a positive semi-definite constraint, and then there is a number of linear constraints. So such a set is called a semi-definite represented set, or I think this is even more specific. It's a spectrahedron. Anyway, and so optimization over such sets is easy, kind of. Yes, thanks. So the solution, for example, for the one-shot communication is expressed as the following SDP. Given the channel, you can, for example, write the Choi matrix here. It turns out that what goes into the formulation of the result is only the support of the Choi matrix. So that means all channels that may give rise to different Choi matrices, but with the same supporting subspace, they will have the same zero error behavior under no signaling. And so it's something like this. So the variables are this S and U, and there are a number of semi-definite constraints. So there's kind of U has to be positive semi-definite, and S minus U has to be positive semi-definite, and then there are some linear constraints. And so the first thing that is nice about this is can be efficiently calculated, and you get also efficient upper bounds, because any semi-definite program, any convex optimization problem has a dual, and for SDPs, the duals are also SDPs, so they are also nice. Let's skip the proof. I don't think you will appreciate this at this moment. The opposite task turns out to be an even simpler SDP. So there, actually, it turns out the answer in theorem 2 depends on the channel. This should be clear when you think about this. For example, in terms of zero error communication capacity, all binary symmetric channels are the same. But the simulation cost